Alright, so this particular video is going to introduce alcohols, ethers, and epoxides. And then we're going to go over some properties as well. So those highlighted red oxygens are kind of just to accent the differences between these functional groups. Um, yeah, I mean, it's pretty straightforward, but it is something that you'll have to commit to memory. So alcohols, we obviously have that OH group on a CsP3 carbon. Okay, so that's what that R group represents. You can have a primary, secondary, or tertiary alcohol, as we've seen in the previous chapters, right? Same with like alkyl halides, etc. And so here's an example of a primary alcohol, and then a secondary alcohol, and then a tertiary alcohol. All right, so there are two other functional groups that are very similar, and that's these two right here. The one on the left is an enol, or as a class, it's an enol and enols, and then phenols or phenols. And these have different reactivity. Notice that OH group is bound to a CsP2 carbon as well, and so that's why they have different reactivity. And so we'll talk about them separately in a different chapter. All right, so ethers are, as you saw above, an oxygen with an R group on either side of it. So you can have unsymmetrical ethers and you can have symmetrical ethers. So an unsymmetrical ether, for example, is like this one. And then obviously the symmetrical is going to have the same functional group on both sides, okay? As opposed to different groups, and like the methyl and the ethyl for the unsymmetrical. Okay, so we can also have cyclic ethers or cyclical ethers, and those could be different ring sizes, but this one in particular is actually classified as an epoxide, okay, or an oxyrane. All right, so let's take a look up here. We've got our CsP3 carbon for our alcohols. And they're all tetrahedral. Okay, so that means that they're going to have approximately a 109.5 degree angle. Now it is going to vary depending on the like steric hindrance around that oxygen, but the oxygen is sp3 as well, and it has that tetrahedral geometry. And so this epoxide, however, since it's in that three-membered ring, it is 60 degrees, and so even though this still has four regions of electron density, it's meaning it's tetrahedral, it's highly strained because that 60-degree angle is drastically different than what the 109 that it wants to be, and this is going to dictate the reactivity of the epoxide, and it's much more reactive than the ethers and the alcohols, and we'll see that later. So for nomenclature, honestly, nomenclature is not something a video should really be made about. It's going to be very brief, and you're going to need to check out the text on your own because it really is just a reading steps, and it's no sense in me really saying it. So I'll do a couple examples, but that's it. So naming is similar to alkanes, however, and so it's just for alcohols, and so we'll add an OL at the end. So like this one would be a cyclohexane, right? But now it has an OH on it, which is an alcohol. So we name it, we take off the E and we add an OL. So it's cyclohexanol. If we add a methyl there, then you start with numbering the alcohol as the 1 position, and then of course you go with the normal nomenclature process of giving the substituent the lowest number. So this is a 2-methyl cyclohexanol, and there you have it. That's pretty straightforward, right? So now there are some extra things to add, like when you have 2 OH groups on there, you would call this a diol. So like 2 alcohols, diol. And so rather than changing to the ending, you keep cyclohexane, but then you add 1, 2 diol because those are in the 1,2 position. So they are wedge and dash, so that is a trans cyclohexane 1,2 diol. Okay, so again, this is just going to take some practice, but it's important that you kind of just see that. So here's another example of a diol, and this is 2-carbon chain, and so it is ethane, and it's a 1,2 ethane 1,2 diol, aka ethylene glycol. So this is your antifreeze, and there are trials, or even maybe more than that, but I think you get the idea, right? You just add the prefix di or tri. So for ethers, we have an unsymmetrical ether here. We have a methyl on one side and ethyl on the other. So what we do is we name them in alphabetical order, the substituents, and then you add ether at the end. So ethyl, methyl, ether. And if it's two of the same groups, you can have diethyl ether. Boom. Very simple, right? These are obviously for straightforward ether compounds. If it gets a little bit more complicated, then it is going to take a little bit more work, but we're applying rules that we already know. So, for example, let's take a look. For one of the first rules is basically name the longer chain as an alkane. Okay, so hexane, pentane, etc., and we'll call that our parent group. Or just as we did our parent group too. So then we want to name the shorter chain as an alkoxy group. So methoxy, ethoxy, tert-butoxy, etc. So that's a methoxy, okay? And this is an ethoxy. So we've seen these before. I try to point them out when we use them as bases. So we have a CH3O minus, and so you can also apply that here when we're naming ethers. So for cyclic ethers, it's just kind of something that I want to point out. These, again, are heterocycles, meaning that they have a heteroatom, or something other than carbon or hydrogen in it. And so this one is really popular, super common, tetrahydrofuran, and this is also abbreviated as THF. And so that's a polar aprotic solvent that we see or will see more, okay? So just pointing that out for you. So moving on to epoxides, we have 3 different methods for naming epoxides, but I'm really only going to go over one. And again, just want to point out that you guys should definitely refer to the IUPAC rules or the text when you're kind of doing these IUPAC or the naming of alcohols, ethers, and epoxides. So the epoxides are probably the most complicated. And so maybe you'll just want to refer to those ones. But there's the epoxy alkanes that I'm going to go over. So if we have a ring, and then you have our epoxide in that ring, or attached to that ring, the epoxide is always the 1,2 position. And we would name that as a 1,2 epoxy cyclohexane in this case. Okay, that's because it's attached to the cyclohexane ring. Okay, if it's not a ring, we number the longest chain such that the epoxide gets the lowest number assignment. And so in this case, it's a 1,2 epoxy, and then the longest chain is a propane, right? So that's our parent chain that we would name at the end, but then at the 2 position, there also is a methyl group. And so that we would have put, just as normal, 2-methyl propane. And so again, these rules are very similar, if not the exact same as before, with the alkanes and the alkyl halides, etc. So we just got to pay attention to the naming and numbering for the epoxy group. So this particular ring right here, we have a cyclohexane ring. We have a 1,2 position for that epoxy group on that cyclohexane ring, and then for the other one, we have a straight chain alkyl group. But we can number this from right to left, giving the 2 position the start of that epoxy group. So if we name the one above, we have a 1,2 epoxy, and at the 2 position we have a methyl group. And then we finish it off with the cyclohexane, right? And remember, we're leaving it the same on this one, just kind of part of the rules. Now let's take a look at the lower one. We have 2 methyl groups or not 2 methyl groups, but 2 alkyl groups with stereochemistry actually explicitly drawn. And so that means that the hydrogens are on the dash form, and so this is a cis isomer of this particular epoxy group. Now, if we number all the way across, we see that we have a hexane. So I wrote cis first, then we have a 2,3 epoxy, and then we have a hexane for our parent. And now we can jam all those together to give us our total name, which is just in that order, but sometimes you might have to combine things together or whatever, and so, but whatever. You've seen me do this before. It's a cis 2,3 epoxy hexane. So, and that's naming of the epoxides, right? So get that practice in for sure. But properties of alcohols, ethers, and epoxides. Oh, let me say though, for the epoxides, take a look at the other naming systems, but I will probably just test you on the epoxy type. Okay, so I say probably. I don't know why I said probably. That's for sure. Okay, so properties of alcohols. This and ethers and epoxy. We already know properties. This is straightforward stuff for us. We're pros at this. The alcohols obviously have the OH group, which have hydrogen bonding, right? But one of the factors that is really big in organic chemistry that we have talked about quite a bit so far is sterics. And so sterics does play a role in reactivity, but it also plays a role in, oh my gosh, I want to get this triangle good. All right, cool. There we go. It does play a role in reactivity and intermolecular forces as well. So as we go from right to left, we have an increased ability to hydrogen bond. And so remember, if you're comparing the same number of carbons to something with less sterics or more sterics, then you are taking into account only the hydrogen bonding ability to determine the boiling point or melting point. And so, because that's going to be the strongest intermolecular force. Now, in this case, the primary, having less sterics, has a higher boiling point and melting point because it has a better ability to hydrogen bond. And as we go from left to right, we have that increased steric hindrance. And you can see that just in the way it's drawn, right? We have 3 R groups on that tertiary alcohol. And we see this when we talk about butoxide as a non-nucleophilic strong base, right? Because of that those methyl groups that are kind of taking so much space, they don't allow that oxygen to do its thing. Same thing for hydrogen bonding in this case. So alcohols, ethers, and epoxides having less than or equal to 5 carbons are water soluble. And we've seen this before as well. So this is nothing new, which is awesome. I love applying old tricks to like new things, right? We don't have to necessarily learn anything new, or we just apply it in a different manner. So that's obviously just because of the oxygen capable of hydrogen bonding. Okay. All right. So there was an error in this video. And I'm not talking about like just misspoke or whatever. This is just a blatant error. So point it out to me, shoot me an email, and then I might hook you up with something. So again, I don't want you to send me like your guesses. I want you to figure out it's a very obvious problem or error, and so point it out to me, and then like I said, I'll hook you up.